Hello, Madison.
Hey, how's it going?
Going well. How are you?
Good.
That's good. Any exams coming up, or is a chill week for you this week?
Yeah, knock on wood.
Yeah.
Yeah, just kind of gonna start like reviewing all the stuff we've been going over lately for OChem
hmm
Out East because we have the next quiz next Friday.
Friday. Yeah, I think so. Next Friday.
Yeah.
Right. Uh-huh.
So
I know, and it looks like it's a lot with this aldol, enolate chemistry stuff, enamine, alpha carbon chemistry. Like it's a lot of reactions.
is it a lot to like memorize and stuff?
Yes, it is. Like the mechanisms are starting to get longer now. Like the each step of the reaction is gonna get longer.
No.
Yeah.
Oh
Right.
gosh, are they harder to predict the products on now
Yes,
because
they
they're
are.
longer?
It is harder to pick the product because like we can't just put on like a chlorine or bromine on the alkene anymore.
Yeah.
We have to like draw out bigger molecules now for the product and like think about what's going on like behind the scenes. But
Uh,
I'll show you like a shortcut on that.
okay.
Right. So let's go through this first. Um, so you first deprotonated the alpha carbon with the
Mm-hmm.
strong base in the first step. That's good to form this enolate ion to put a negative charge on that alpha carbon right there. Once you have that, then this is our nucleophile right here that's going to attack this electrophile carbon and push the one to the oxygen, which would give us this. So this right here would be the carbonyl carbon. This right here would be the starred carbon, and that would be the new bond between them. But this molecule here does not have this carbon because that is a hydrogen, and we have to maintain that as the hydrogen like that. Right.
Okay.
Uh-huh. So from here, this oxygen here also has a negative charge because it has 3 pairs of electrons and a single bond, which is going to be protonated by the water to become neutral OH like this, right? So this right here would be water. Now the next step here, this OH minus will not attack the carbonyl carbon or this oxygen here. It's going to deprotonate this alpha carbon right here.
Okay.
This is also an alpha carbon, right? Because it's one carbon away from the carbonyl carbon. Like this is an alpha carbon, this is an alpha carbon. But we're interested in the alpha carbon that is in between the carbonyl carbon and alcohol, right? Because that's the most, you could say, partial positive carbon, right?
Uh-huh.
It has the most partial positive charge, because it is in between the two electronegative atoms we have, alcohol and carbonyl, right there.
Right.
So draw out one alpha hydrogen, have this OH minus grab that alpha hydrogen, make a bond right here between the alpha carbon and carbonyl carbon, and push the double bond onto the oxygen like that.
So ignore the red arrows essentially.
Yes, ignore the red arrows
Okay.
and look at the blue arrows where we're grabbing the alpha hydrogen in between the two alcohols, I mean two oxygens, one alcohol and one carbonyl, right, in between the two oxygen atoms. The bond between the hydrogen being grabbed and carbon is going to move over to make a double bond between the carbonyl carbon and alpha carbon. Make a double bond right there, which will push this double bond onto the oxygen right there.
I see. Okay.
Mhm. Which would then give us this intermediate here, but this is a hydrogen, which we can leave as invisible. So you could draw out the hydrogen, or you can leave it as invisible of the benzaldehyde. And
Hmm.
then from here, once we have that, then we could move the negative charge oxygen down to make a double bond again, like reform the carbon double bond oxygen that we had earlier. Shift this double bond over to make a double bond over here between the alpha and beta carbon, and then kick out the OH group. Right.
Alpha, and then beta, and then you're gonna kick out your OH group. Okay.
Yep. And that's gonna give us this final product where we don't have the OH group anymore because it got kicked out, and a double bond between the alpha and beta carbon, like that. Right.
Oh, so the bond got moved over then. Okay.
Yep. And if I draw that out again, it would look like this with the benzene here. And this is a hydrogen, so I'm gonna leave that as invisible. There's a double bond right there. And we could draw the carbonyl like that.
Mm-hmm.
Right. Like this whole thing here is the exact same thing as this right here, just redrawn.
Right.
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 But we don't stop there because you know how they give us two equivalent of the benzaldehyde? The reason why they give us two equivalent of the benzaldehyde is because we could do this mechanism one more time. So we're gonna practice this, and you're gonna describe to me what happens in the mechanism here. It's okay if you get stuck, just let me know. And then make the mistakes now, so then you could catch it, and then we can move on how to predict the product quickly. Right. So let's say we have this um uh, uh, alpha beta unsaturated carbonyl, and an OH minus is floating around. What would this OH minus do to this whole molecule here? If we want to do this mechanism one more time, let's say. Right.
OH minus, it's gonna want to attack one of the alpha hydrogen,
Yep.
which would
Alpha.
be the hydrogen that is alpha to the carbonate.
To the carbonyl. We have this alpha hydrogen and this alpha hydrogen, but we're gonna go for this one here because we want to make a double bond right here, or a negative charge right here instead, right? Because that's gonna give us that negative charge right there.
Okay.
Right.
And why do we want the negative charge there? Because the other one is more substituted?
Yeah, because if you think about this one here, if we, let's say, grab this alpha hydrogen over here and make a double bond right here to push that double onto the oxygen, we would have a very unstable molecule named an allene. So we're gonna have like something like this, and like two double bonds right next to each other like that. If we deprotonated that alpha hydrogen instead, right? So that's why we don't want to make a double bond right here because there's already a double bond right there next to it. So we don't want that there. But we do want a double bond here. But we, like you drew it earlier, this is how I always drew it. Like put the negative charge on the alpha carbon because it's clear to see where the nucleophile is, right?
Right.
And hopefully she gives you full credit for the mechanism because you know how Levens wants you to draw resonance structures for mechanism anyway. It might be safer to if you drew it like this. Like if you drew the OH minus, grabbing one of the alpha hydrogens like you did. Make a double bond right there and push that double bond to the oxygen to give you this intermediate right here, which is the same thing as what you did up here, but it's just a resonance structure of that, right?
Okay.
But the way that you drew it is more clear to see where the nucleophile is, which is this alpha carbon right there, like that.
Right. Okay.
This one here is kind of misleading because that is not the nucleophile, even though there's a full negative charge on the oxygen atom. Right. Okay.
Do you mind going over? Oh, I think I missed that part. The H. Oh, just the on the other part. Just that's negative. Okay.
Yep. The purple part of the how we generated
one more over. One more to the right. Yeah, that one.
Right. This one here. Yeah. So this one here. The O minus grabs the hydrogen from the water, and then when we want to draw out the arrow like specifically, this is what it would look like. The bond between this hydrogen and oxygen being grabbed is going to move on to the oxygen right there, right? I think if you draw like this anyway, it'll be still accepted as full credit, but it looks like your arrow is starting from that hydrogen right there, but it's still aside from that bond right there because it's the movement of those two electrons in that bond right there.
Okay.
Right.
Yeah. Okay. Perfect.
Yeah. Yeah. So you know how it's very specific, like very nitpicky on the mechanism, like all the arrows, movement, and charges, and how you draw things. Yeah. Right. So the next thing here is that we're going to grab this alpha hydrogen right here, and you could do it both ways. You could do it your way, which is what I did when I took the class as well, or we could do the safe way for Levin's class, which is like make a double bond here, push the bond to the oxygen, and then draw the resonance structure, just to make Levin's happy, right? So let's do that. But know that the nucleophile is on that alpha carbon right here, where the hydrogen was at. Negative charge is gonna be there. Right. And we're gonna draw that too. Like let's actually just draw that. After we draw this, enolate ion, we could push this negative charge down to make a double bond there, and push that double bond to that alpha carbon to give that carbon a negative charge right there. Okay.
Boom, boom.
Boom, 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 like that. Right. So now once we have this resin structure right here, this is our nucleophile. We have two equivalents of the benzaldehyde. We already used up one of it. This is our second equivalent of benzaldehyde right here.
Mm.
What would happen next between these two molecules?
Is it the addition?
Addition step, nucleophilic acyl addition.
Yeah.
Where
Yeah.
our nucleophile here, the star, is going to attack our electrophile dot right there, that partial positive carbonyl carbon. Right? But what other error has to happen when we do that attack? When we try to make a new bond between this starred atom and that dot atom. Right
What
there.
other arrow?
Yeah, because imagine if we did make that new bond right there between the star and dot. There's gonna be a problem for the dot carbon.
There has to. It's gonna be like, its octet is gonna be too full.
Yes,
so
too
it has
full.
to break off the bond to the oxygen.
Yes, like that.
Okay.
Correct. Right. So, yeah, I like how you explained it. Like, it's better to understand like why this error happens. You know, like you're doing this mechanism problems, like
Right.
understand why. It's because of the octet row being too full, so we want to conserve it by pushing it over to the oxygen. You know. Now to connect it, we could just connect the star and dots. I'm gonna draw out the star molecule like this. And this right here is the new bond between the star and dot. That's the new bond between them. This dot here is attached to a hydrogen, but I'm gonna make that invisible hydrogen. A benzene, which is this benzene here. It was double bonded to an oxygen, but it is now single bonded to an O minus because we pushed one of the bonds onto the oxygen, giving it a negative charge, giving it that oxygen a negative charge.
Okay.
Okay. What would be next here?
We're gonna we essentially want to make that O minus a double bond O and like make it stable, correct?
This O minus here, we eventually want to make it neutral OH, and then later kick it out in the mechanism, right? Because eventually in the final mechanism, this carbonyl here, we want a double bond between the alpha and beta carbon right there, and get rid of that OH. That will eventually become OH like that.
Okay.
Right, and this is what we call an alpha beta unsaturated carbonyl. Right, and it's called that because if you look at the carbonyl and its alpha and beta carbons, in between the alpha and beta carbon, there's a double bond there, aka unsaturation there, right? And in this reaction, aldol dehydration, we want this alpha beta unsaturated carbonyl and get rid of that alcohol right there. But first, we gotta make this neutral somehow. How can we make that O minus neutral?
We have to grab the H from our side product.
Yep, or solvent, water here.
Okay, is that a
solvent? Yep. It's our solvent because it is included in the arrow as H2O, and we have plenty of that. You can also call it as a side product because we did also grab H from OH minus. So it's a side product, which is our solvent here.
Okay.
Yeah. Okay. You could call it our proton source because it's providing a proton, a hydrogen, to this oxygen here.
Right. Okay.
It's not H3O plus or H2SO4 because we don't have that in the reaction at all. Right. Okay. Now once we have this OH here, how can we then get rid of this OH and put a double bond right here? This is what I call a boomerang step here. Like this part of the mechanism is the boomerang step. And I'll show you why. Because you know how like this excess amount of OH minuses, and I'm gonna draw this alpha hydrogen here between the OH and the carbonyl here. We could have just like grabbed that alpha hydrogen, make a double bond there, and kick out the leaving group like that to get the final answer right away, quickly.
Right.
Right? But they don't want that. They don't want that as a mechanism. they want to show the enolate ion being formed first. So when you grab that alpha hydrogen, make a double bond right there, push the bond into the oxygen to form your enolate ion one more time. They want to show that enolate ion for some reason. I think it's because it is stable, so it's gonna form that first before kicking out the OH. Right. So once we form this enolate ion here, then we are going to make a double bond here between the carbon and the oxygen, shift the double bond over there, kick out the OH to give us our final answer. But we could have reached that final answer earlier, but we went the long way to show the enolate ion.
Go there, and then that's gonna go there. This might be a silly question, but what happens to like whenever that OH is kicked off, it just is like our side product?
Yeah, it kicks off as the OH minus side product, and it
Okay.
just floats around like that. And you would have
Okay.
to probably draw that out in mechanism problem when it gets
Oh,
kicked out. Like draw
okay.
out everything that gets kicked out. Draw all the side products for mechanism.
Okay.
So let's look at this final answer here. We could have reached there from, let's say, drawing the arrows in blue like this. Grab that alpha hydrogen, make a double bond right there, kick out the OH, and that would directly give us this final answer right there. Yeah, but we don't do that for mechanism. We want to show this enolate ion here. Right, which is the purple highlighted part of the molecule. An alkene next to an O minus. Enolate ion, like that, in the mechanism.
Okay.
Okay. Now I'm gonna give you a practice problem for you to try to predict the product and the mechanism. Here, I want you to help predict what the nucleophile is and what the electrophile is gonna be here. Right, so let's do this here. Okay, and do that. NaOH, H2O, heat. Okay. Let's do one equivalent of this. Just do it one time because that's gonna be more likely for the electric quiz. One equivalent.
Just to predict the product or the whole mechanism?
Both.
Oh
Both.
no. Okay.
Yeah, do the mechanism first, leading you to the predicted product.
Okay.
Yeah. Okay. And then when you do that, I'll get back to you so that we can check your work.
Okay. Sounds
Okay.
good. All right. Thank you.
Yeah. Hey Wiley, hey Layla. Did you guys have a question or topic you guys wanted to go over today?
Yeah. Can you go over Wittig's reaction?
Oh, the Wittig reaction. Yes, that's the
Yeah.
weird one with the
The illid,
illid.
right? The illid? I don't know how to say it.
Illid, like something like this, right?
Illid.
With the
Yeah, with the Y.
Y.
Yeah.
And the carbonyl.
Yeah, yeah.
I remember this reaction is with the illid plus carbonyl, and that gives you what does that give you again? Carbonyl.
It's supposed to give like an alkene.
An alkene, yes, that's
Yeah.
right. A carbon double bond carbon. And the illid, the carbonyl is a carbon double bond oxygen, and alkene is a carbon double bond carbon. The illid is the weird one. It was like a pH3.
Yeah.
Something like
And
that.
then, yeah, like fragments of
some fragments of that.
Of like.
Yeah.
It's like a double bond to carbon with like your stuff attached to it.
Right. Like different fragments attached to the illid and carbonyl. Let me see here. Okay. Oh shoot.
Is this an important reaction? Like if you did it 118B or something? Or
this is a important reaction at the end of 118B. The mechanism is very weird here. Right. And so
yeah,
this is R.
it does like
C,
a double arrow thing to form two double bonds.
Right. Okay, I'm gonna do this here. I'm gonna highlight the illid carbon in yellow, like this, and highlight the carbene in blue like that, the product is gonna have the alkene where the two carbons are coming from the ylide and carbonyl,
Uh-huh.
right? So for one practice problem, let's say we have this benzene with the aldehyde, and we have this ylide here, PPH3, attached to a carbon with some random R group. And the Wittig reaction, right? Did he go over the difference between the Z alkene and E alkene for this reaction, or did he just go over the major product is the Z alkene?
Let's see. He said it's the Z alkene for the unstabilized ylide and E selected for the stabilized.
Okay, he did go over the difference between them then. Okay. Okay. So let's go over that too. For unstabilized ylide.
I don't even know what that means. Unstable. Like he just like said it.
Oh, okay. That means if the ylide can do resonance, basically. So
Oh, okay.
if your ylide right here, which is this one here, can do resonance, then our major product would be the E alkene. But in this case, our ylide cannot do resonance. It's unstabilized because this double bond here can't move over there to do resonance. But let's say, for example, you had like a conjugated system right here, which can like, move the double bonds over and do resonance like that. This is considered a stabilized ylide because it could do resonance. It's delocalized like that.
Okay.
Right?
Okay.
And then that would lead you to the E alkene. Yeah.
E alkene. Okay.
For stabilized ylide. Okay, let's predict the product first and then worry about the mechanism later because the mechanism is very weird.
It's really long.
Yeah. So here is our carbonyl. The first thing I would do is I would locate my carbonyl carbon, which is that right there, and my ylide carbon, which is that right there. Then I would think in my head that I'm getting rid of the carbonyl, getting rid of that carbon double bond oxygen, and getting rid of that ylide, carbon double bond phosphorus triphenyl group. And I'm just gonna connect these two pieces together, the yellow and blue carbon, right? And when I connect them, I'm gonna first draw out the benzene with the yellow hydrogen, like that. I'm gonna leave the hydrogen here invisible of the benzaldehyde, right?
Okay.
I'm gonna make the new bond between the yellow and blue carbon because that's where my double bond is gonna be at, right? And now from here, once I have my double bond, I then think about what kind of major product I'm gonna get. Is Z alkene or an E alkene? Right, and I look at that by look at the ylide. Is it stabilized or unstabilized? Right, it is unstabilized because it can't do resonance. So Z. So my methyl group here, the R group, would it go up or would it go down for the major product?
Okay.
So if we want the Z alkene, our major product would have the methyl group going down because that would lead us to our Z alkene, where the two product groups are on the same side, like that. Right. Now, let me give you an example here, but with a stabilized ylide this time. Let's say we have this aldehyde, and we have this ylide right here. Okay, I want you to predict the product here, and then once you have it, send me the picture on Zoom or Discord.
Yeah.
Hey Layla, is there any topics you wanted to go over for 118B after this ylide reaction and mechanism after I go over it?
Honestly, I think that Ald's D's, wait, I don't know how to say it.
Oh, Diels order.
Yes, that one
Yes.
so much sense to me.
That one, yeah. There's a lot of things that goes on with that reaction. I did go over predict the product for the last 2 office hours, but I didn't explain everything in detail, like step by step, because I just assumed that they already knew the steps, which I think they did. But I can't explain the reaction step by step.
If it takes too long, I can also just like look back at the other ones. I just wasn't sure if it was in the other ones.
Oh no, the other ones like wouldn't like teach you Diels order from scratch. The other ones just assumes you know it already, and it's just practice, like the other ones. So I gotta still teach it from scratch. Yeah, which I can do here. but it's gonna probably take some like a while to do it. So I'll probably do that tomorrow's office hours at the beginning.
That's fine. That's fine.
Yeah,
Thank you so
uh-huh.
much.
Yeah, of course, Layla. Because Leo's order for the next midterm is gonna be the longest reaction to learn, like the hardest reaction in my opinion. Once you get to electrocyclic reactions, which we could go over today, like with the thumb rule, crown-rotatory, dis-rotatory, that's easier to pick up. So we'll do that today. The electrocyclic ring opening.
Sounds good. Thank you.
Yeah. Oh yeah, in medicine, when you have the mechanism and predictive product ready, you could also send it to me through a message as well.
Okay, sounds great. I haven't really started it. I'm still looking at the first one we just
Oh
did.
yeah, it's okay, it's okay. Right. To give you a hint, think about what's happening in the first step. What ion are we forming? And think about which one of the two molecules that I gave you has that thing that we want to make that ion.
Okay, thank you.
Uh-huh. Week 7. Oh my gosh. Midterm 2 or what midterm seasons are coming up again, week 8, week 9 probably. Okay, I see. Yes. So you put this alkene, which is the Z alkene, right? And if we highlighted this carbon in yellow and this in blue, this ylid carbon in blue, that would be this right here. But let's look at the ylid here. Can this double bond of the ylid do resonance with the carbonyl here, let's say? Yeah. It can, right? And because it can, this is considered a stabilized ylid. And what we predict the product here, our major product would be the E alkene, right? So you could keep it the same, but you could shift the methyl group going down like that.
Yeah.
E.
I drew it weird. Like when I
alkene.
I started from building the alkene first and then added the stuff.
I see.
I completely forgot.
Yeah. All right. That's probably the most tricky part to remember, like
Yeah.
the E versus EZ alkene. Yeah. Right. Okay, so that's how we predict the products for Vidic reaction. Predicted product, not that bad. But what is bad is the mechanism, the weird, like, I don't know, like migration arrows. So let's look at that really quick. Okay, so let's look at the first mechanism that we did with the benzaldehyde and the ylid with the methyl group like that. I'm gonna draw the resonance structure of this ylid where I'm gonna push the 2 electrons of that bond onto the carbon to give that carbon a pair of electrons and a negative charge, which would give this phosphorus a positive charge like that. Okay, now this carbon here with the negative charge is my starred atom, which is my nucleophile. This carbon here is my carbon, which is my electrophile. I'm gonna have my nucleophile attack my electrophile, and that's gonna break the octet rule, right? If we try to make a new bond between the star and dot carbon, the dot carbon will have 5 bonds. 1, 2, 3, 4, 5. That's not good. To conserve the octet rule, we're gonna push the double bond onto the oxygen to make a single bond O-, which is gonna give me this intermediate here, like this. So this is my dot carbon. This is my new bond between my dot and starred carbon. New bond. The dot carbon is attached to a hydrogen here, right? But I'm gonna leave that as invisible. I'm not gonna draw that hydrogen out anymore. This dot carbon was double bonded to an oxygen, but it is now single bonded to an O-. This starred carbon here is attached to a methyl group, which I'm going to draw down here because I know eventually there's going to be a double bond between a star and dot carbon, and I know my alkene is going to be Z because this is an unstabilized ylid. So that's why I'm putting the methyl group down here on the same side as the benzene right there. Right, and then this starred carbon here is also attached to this phosphorus triphenyl group with the positive charge right there. Okay, and I'm drawing it in this form to show that this O- here is attracted to this positively charged positive phosphorus because opposite charges attract. So this O- here is just gonna attack that phosphorus to form this cyclic ring here, this 4-member cyclic ring where we have oxygen and phosphorus part of that 4-membered cyclic ring like that. Okay, now think of this conceptually. Oxygen and phosphorus are extremely attracted to each other, so they want to leave in the molecule and make a double bond with each other to become even stronger, right? So this is going to be, think of it as our leaving group. They want to leave from the molecule.
Yeah.
And to do that, this is what we could do. We could have one of the bonds, doesn't matter which one, here or here, break and make a double bond between the oxygen and phosphorus like that, which is going to have this other bond here break off as well and make a double bond right there, which forms our alkene and kicks off the whatever the side product is called, giving us our final Z alkene. It could be E if your ylid was stabilized to the resonance, but in this case it's Z because our ylid here is unstabilized, and our side product would be this oxygen double bond phosphorus triphenyl. There's a name for that, but I forgot what the name of that is. It's called a triphenyl phosphine oxide, but I don't think did he go over that, like this side product that left as well, the mechanism, this
Yeah, he wrote that.
Okay.
Triphenyl phosphine oxide.
Oh, he wrote that the whole thing down too. Okay.
Yeah,
okay.
he might test us on it. Where
Yes,
he's
yes.
like, yeah.
Yeah, know it for sure.
Like on
then.
the vocab section, he might give us like oxaphosphatine and
Yeah.
explain what it is.
Yeah, right.
Or like the intermediates. Oh.
Yeah, the intermediate. Yeah. So know it for sure then. Phosphine, because Beal, like I remember you telling me that he wrote it one time and it showed up on the test. So everything in his test, like in a spare game, like whatever he writes down, So because he wrote this down, know this what this is its name as well. Yeah. There is a quicker way to draw the mechanism here, where instead of drawing out the resonance structure like that, you could have done something like this. And let me do the E alkene this time with the 1, 2, 3, propanamide, the propanal, daldehyde, propanal, propanal. And let me draw out and I'm gonna make it go like this. Oh, actually, phosphorus like this, pH 3, boom, and this carbon here was attached to this group right here. I know that in the mechanism, when I draw the resonance of this ylid, there's going to be a negative charge on this ylid carbon right here, which is my star. And I know that that carbon to carbon is my electrophile, which is my dot. So instead of drawing out that resonance structure like we did earlier, we could just directly have the star attack the dot, and at the same time simultaneously, since we note that we're going to push the bond onto oxygen, giving that oxygen a negative charge, we don't have to draw that out, right? We could just draw that O- attacking the phosphorus at the same time, because we know that phosphorus is going to have a positive charge in the intermediate behind the scenes, right? So you could just go directly like that, which is going to shorten the mechanism, but it does the same thing. This is my dot. This is my new bond between the dot and star. And because this is a stabilized ylid, the R group, I'm going to draw up here, which is on the opposite side of that R group of the aldehyde, like that. Well, it's kind of weird because we know that there's going to be a box structure like that, and this looks very weird. But the reason why it's up here and why it makes an E alkene is because there's a lot of p orbitals here, right? The reason why it's able to do resonance is because of delocalization between a network of adjacent p orbitals that are able to do resonance. And because of those p orbitals, they prefer to be close to the other p orbitals here to increase resonance, increase conjugation, right? This right here looks very weird because there's a lot of steric hindrance. But in OCHEM,
Okay.
resonance overpowers steric hindrance. So the two big factors in OCHEM, resonance and steric hindrance. In most cases, resonance beats steric hindrance as a factor, right? So even though this looks very sterically hindered and unstable, it will be like this E alkene because of resonance, increased resonance, like that. Okay, so now that phosphorus is also attached to pH 3, like that. Now we just do that two-step migration thing to kick out that triphenylphosphine oxide, and create our E alkene. Like that. Okay, that's good. Now let me give you one more practice problem for you to practice the mechanism and predict the product for. Actually two, one for E and one for Z alkene, and then we'll move on to electrocyclic ring opening and ring closing for 118B. Okay, let's give you that, and let's also give you this right here. So predict the product for these two reactions, and for practice, draw out the mechanism as well.
Okay.
Okay. Okay, so Layla, for us to go over the electrocyclic reactions, I'm actually gonna pull up the AATC Muir-Jones worksheet on that.
Thank you.
Yeah. So let me actually pull up this as well. Right here. Okay. So electrocyclic reactions is a type of pericyclic reaction, just like Diels order, but it is way quicker to learn than Diels order. There's two types of electrocyclic reactions. There's ring opening and there's ring closing. The mechanism is going to be very short, as you're going to see soon. But here is the table that I would put on your note card. The two tables there. One table he gives you, another table that is very useful when predicting these products here. You could either see 4n electrons, which is what he shows you, or you can think of it as an even pair of electrons. Right, pair of electrons. Or you can have 4n plus 2 electrons, which is going to be an odd pair of electrons. And there's going to be two different reagents. Delta symbol is heat, and H nu is light. And that's going to change what the product looks like. Change the reaction. Right, and I'm going to put con for con rotatory, and this for this rotatory. Yeah.
I don't
Yeah.
know.
Mhm.
Oh, sorry, I got unmuted, I think.
It's okay. Yeah, I thought you had a question. Yeah. So when we rotate groups, right, we're gonna rotate them either con rotatory to each other, which means those two groups rotate same direction. Con rotatory rotate same direction. This rotatory, we're gonna rotate opposite direction. Okay, now the direction that we're gonna rotate in is going to be either clockwise or counterclockwise. Right, and when I first learned this reaction, this was the trickiest part, to tell the difference between clockwise and counterclockwise with the thumbs. But we're gonna practice that. Right, now another chart that can help you is the thumb rule chart. Right, and there's gonna be different scenarios depending on the reaction. Ring opening versus ring closing, where you're gonna start your thumbs a certain way and you're gonna end your thumbs a certain way. Okay, so when you're ring opening, you're gonna start your thumbs up or down for wedge or dash, and you're gonna end your thumbs left or right. When you're ring closing, you're gonna start left or right, and you're gonna end your thumbs up or down for wedge or dash. Okay, so right now it looks like nothing is going on here, but then let's do some practice to make it more clear. Let's do ring closing first, and then a ring opening after, as an example. So for ring closing here, let's say we have something like this with that group, and this reacting with heat or light. And I'm giving you two different scenarios because this will give us two different products here. You know that you have ring closing when you have no wedges or dashes on the reactant. And I'm going to draw out the arrows here for you. Right? This double bond here is going to make a single bond between that carbon and this carbon, shifting this double bond over to make a double bond right there. So to keep track of things, we can number them 1, 2, 3, 4, like that, which is going to give us this base products right here. Which this is going to be 1, 2, 3, 4, 1, 2, 3, 4, like that. Does that make sense so far, Layla, on how I got to those base products, or does anything not make sense from there?
Could you explain like one more time how you got to that?
Yeah, so we see that there's no wedges or dashes here on the reactant molecule, so we know we're not gonna do ring closing. I got to here by seeing that this double bond here between 1 and 2, I'm gonna move that double bond between 1 and 2 based on this arrow to make a single bond between 1 and 4. So that yellow highlighted bond right there between 1 and 2 is this yellow highlighted bond right here between 1 and 4. Right. That's where the new bond between 1 and 4 came from. Before, there was no bond between 1 and 4, right? No bond at all. But we created a bond connecting carbons 1 and 4 from this arrow here, moving that double bond between 1 and 2, which is why we don't see a double bond between 1 and 2 anymore, right? Before, 1 and 2 had a double bond, but it's gone now because we used that double bond to make that single bond between 1 and 4.
Okay, so you can just like move the electrons around to make a new bond. That's why there's not a double bond anymore.
Right, between 1 and 2 and 3 and 4. There's no more double bond between 3 and 4 anymore, but there's a new double bond between 2 and 3, which came from the double bond between 3 and 4, like that. Right, and that's called ring closing because we closed the ring, creating a ring here. Before, there was no ring like in this part of the molecule here, but we created that ring, which is called a ring closing reaction, like that. Right. Now, if you look at carbons 1 and 4, 1 and 4 has those R groups right there. But how do we tell if, like, let's say the R groups are going to be both wedges, or if they're going to be both dashes, or if one is going to be wedge, one is going to be dash, or vice versa, right? Because it could go a lot of combinations. The way that we tell that is using the reagents here and using the charts that I gave you earlier, right? So that's the hardest part of this reaction here. Now, how many pairs of electrons do you see are interacting here in the mechanism? How many arrows do you see in this reaction? 2, right? And that's an even pair of electrons. So let's focus on an even pair of electrons and heat. If we look at this chart right here, we have an even pair of electrons moving and heat, which is going to be a con-rotatory reaction if we use heat. If we use light, then that would be a dis-rotatory reaction, right? So let's write that down so that we don't forget. This top part here is con-rotatory. This bottom part here is dis-rotatory. And don't associate a heat with con-rotatory and do not associate light with dis-rotatory because it could be reversed, right? If you had like an odd pair of electrons, for example, let's say. Okay. So now once we have that, let's do the thumb rule. Since we're ring closing, we're going to start our thumbs left or right and end our thumbs up or down to show wedge or dash. We see that if we look at this carbon 1 right here, it is going up. And that group is going up. At carbon 4, this group is going down. They're going on opposite directions. They're trans to each other. They're going in opposite ways, right? So let's do the thumb rule. I'm gonna say that my left thumb here is the ethyl group on carbon 1, going to the left side. That means my right thumb here is gonna be the methyl group going to the right side. Right, so I'm gonna start my thumbs like this. And when I rotate my thumbs, I'm gonna stop at either on the top or the bottom. And I get to choose what direction I'm gonna rotate here, clockwise or counterclockwise. Let's say I rotate clockwise on my left thumb. I stop at the going on top, right? That means that if this is con-rotatory, I would also have to rotate my right thumb clockwise, which goes down. And I stop going down, because I end my thumbs up or down. I see that these two thumbs here are trans to each other. One is up, one is down. So this ethyl group here is an ethyl group. This methyl group here. Wait, this ethyl group here is a dash. This methyl group here is, this ethyl group here is wedge. This methyl group here is dash because of the thumb rule and plus minus because it could have been the other way around. This could have been dash. This could have been wedge. So that's how you tell the stereochemistry for these electrocyclic reactions. Let's do the same, but for this time for dis-rotatory. Start our thumbs the same way, clockwise. This will have to go counterclockwise. So now they're facing on the same side. So both would be wedge or dash, plus minus. Okay. Any questions on that, Layla, on how I got to these products here? You should also try it with your thumbs too, like practice with your thumbs too, to make sense of the chart and how we're getting to here.
Yeah, I think I just need to practice it. So it's just basically off that chart.
Yeah, off this chart. And I gave you ring closing example. There's also a ring opening example, but I remember making a video on this with office hours, focusing on electrocyclic reactions on all the office hours, like back in spring 2024, I'll send you that video to watch for you to practice as well. I'll find that video. I send it to you.
Much.
Yeah, of course. Okay, so Madison, let me check your work here. You had
I got stuck on where it attaches because I feel like the other problem, it was easier to understand like where it's supposed to attach with the hydrogen,
right.
like how it flips and
You
attaches.
Oh yeah. So when we grab the hydrogen, we're grabbing the alpha hydrogen. So you drew out the alpha hydrogen of the carbonyl here, right? Of this carbonyl here. But if we look at the alpha carbon here, this alpha carbon, right, has no alpha hydrogens because there's no hydrogens attached to this carbon here. Alright, like this is a carbon, 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 carbon. And it's already bonded to 2 4 carbons.
It's bonded to a carbon, not hydrogen.
Yeah, it's bonded to a carbon, not hydrogen, right? So this right here is not gonna be our nucleophile. This is gonna be our electrophile right here. That carbon carbon of the aldehyde right there. It's gonna be attacked. Right? But what about this other molecule here? Does this molecule have an alpha hydrogen?
No.
Okay, so let's look at the carbonyl carbon here. These are 2 alpha carbons. These 2 alpha carbons here, are there any hydrogens there? Any invisible hydrogens?
Yes.
Yes, right. There's 2 here and 2 here.
Mm-hmm.
And because they're symmetrical, it doesn't matter which one we're gonna grab. Let's say we grab the left one here. I'm drawing out the 2 alpha hydrogens there. OH minus here. We're gonna grab that alpha hydrogen and let's do it the Levens way where we generate the enolate ion, right? That bond between the alpha hydrogen and alpha carbon being grabbed is gonna make a double bond right there, which pops the double bond onto the oxygen like that,
Okay.
giving us this intermediate here.
So that's the electrophile?
This is gonna be our nucleophile. When you see enolate ion, think of nucleophile, right? But it's not this O minus, that's the nucleophile. It's this alpha carbon, that's the nucleophile. Because you know how when we're grabbing this hydrogen here and we're giving this carbon a negative charge, like you could think of like that. That's the easier way to think about it, right? Because that carbon there is going to be negatively charged, which is going to attack some positive charged electrophile. Because
Okay.
nucleophiles always attack the electrophiles, and nucleophiles are negatively charged. This right
Okay.
here is our electrophile. This positively charged, partial positively charged carbonyl carbon right there is our
Mhm.
electrophile that will get attacked eventually.
Okay.
Now let's draw out the resonance structure of this by shifting that down to make a double bond there and giving that alpha carbon a negative charge like that. Right. To clearly show where the nucleophile is at, which is at that alpha carbon right here, which I am gonna star right there. That is our nucleophile. The negative charge. So nucleophiles negatively charged, electrophiles positively charged. Right.
Okay.
Okay, so now let's bring in our electrophile. The aldehyde with no alpha hydrogens. What would happen here between this star nucleophile and this dot electrophile here?
Don't they? That's like the point of attachment.
Uh-huh. But who attacks who here in the mechanism? Like,
The nucleophile.
Mhm.
Nucleophile.
right, we start
Attacks
from the
the
nucleophile and go toward the electrophile. Right, a common mistake is like people start from the electrophile and attack the nucleophile.
Yeah,
But-
I'd want to do that.
Yeah, we don't do that. We don't do that. That's not good. That's unacceptable. There's nothing to move there. Well, that this is what we move. That pair of electrons negative charge right there, like that. Okay.
Why can't you go the other way?
We can't go the other way because there. Well, you can technically put a negative charge on that carbon and a positive charge on oxygen, and then that negative charge can move, but we can't go towards that carbon right there because this carbon
Mhm.
is a nucleophile. It has pairs of electrons right there.
Okay.
We go the other way because when we draw arrows, the arrows show the movement of electrons. We see those 2 electrons can move towards this positive charge carbonyl carbon here, which would move this bond onto the oxygen right there. Right, so in OChem, nucleophile will always try to fill in the void, the electrophile. It will go towards something positively charged. Right, the negative charge
Okay.
here is going to go towards that positive charge, which would also push that double bond onto oxygen at the same time to conserve the octet rule.
Okay.
Okay, now let me see how you connected the molecule here. Okay, so what did you do? How did you get this product here?
I don't know. It's pure guess. I'm being
Okay,
honest.
no. Okay. So that's why you star and dot it, Madison. That's why you star and dot it. So this is the star molecule here. This is the new bond between the star and dot molecule right here. Right? Does that make sense so far?
Yeah.
Right. This new bond here comes from this arrow. When this like nucleophile attacks that carbon, that's making that new bond right there. Now, what is attached to this dot carbon here?
The carbonyl.
It was attached to the carbonyl, the carbon double bond oxygen, but it's no longer double bonded to oxygen. What is it now after we pop that double bond
It's
onto
a
oxygen?
single oxygen.
With a what charge?
Negative charge.
Yes, negative charge. Okay, that's one thing attached to the dot carbon.
And then it has the 3 substituents, 3 other hydrogens.
Butyl. Wait, this is not hydrogen. These are carbons.
On the
Right.
oh yes.
Yeah, these are carbons. So this whole thing right here is a tert-butyl group right here. These are CH3s. Right. And this is a hydrogen, but we don't have to draw that out. We can leave it as invisible.
Okay, I see.
You can draw it out. It won't be wrong, but it will make things more crowded.
Okay.
Okay. Now, once we have this intermediate, what do you think is going to be next?
I think we're gonna have our side product. It's gonna come in
our
we should have the
water.
OH.
Yep.
And then
minus
that's
grabs that. Yep.
gonna get. Is it correct to say that gets protonated?
The O minus or this water.
The water.
The water here is getting deprotonated. It's losing a proton. It's losing a hydrogen.
Okay.
The O minus is getting protonated because it's gaining a proton, gaining a hydrogen. Right.
Okay.
Yeah. So water deprotonated, O minus protonated. And that would give us OH minus as a side product and this intermediate here. Okay. Now, boomerang step. How would the arrows look like for the boomerang step here?
Okay.
We're gonna do another acid-base reaction, and we're gonna be interested in an alpha hydrogen. But there's 2 alpha hydrogens that we have. But which alpha hydrogen are we interested in? Are we interested in alpha hydrogen A or alpha hydrogen B?
You want alpha hydrogen B because it's less substituted?
It is less substituted, right? But it's not as acidic as alpha hydrogen A. It's not as positively charged as hydrogen A, right? Because let me draw out A here and B here. The OH minus is attracted to a bigger positively charged hydrogen, right? So that A has a bigger positive charge than this B because this A here is next to, in between those 2 electronegative oxygen atoms right there, right? So these 2 oxygen atoms here are withdrawing electrons from that A, making it more positively charged. It's making this HA lose electrons, lose negative charge, which is gaining more positive charge. Whereas this HB here is only next to 1 oxygen atom, pulling on its electrons. So that's why it's not as positively charged. It is still positively charged, but not as much as HA, which is in between these 2 oxygen atoms here, pulling on its electrons. All right. So that's why we're interested in the alpha hydrogen in between the 2 oxygen atoms. So this OH minus here is going to grab that HA and then generate our enolate ion like this. Right. So this mechanism here, you notice how it's like very long. It's just law of practice, you know, like go step by step, practice and explain, talk yourself through it.
It's essentially the same steps for just different problems.
Yeah, like there's different decorations, different R groups.
Same things, yeah.
Yeah.
Like you can apply the steps in this one to like a different problem of this similar nature.
Yes, right. You could do that.
Okay.
Just focus on what's important here, and everything else is decoration, copy paste. But those decorations are like very tricky sometimes because they could like make you confused, for sure.
Yes.
Yeah.
Definitely very confusing.
Yeah.
Like learning it.
Right. Then the last step here, this O minus here would go down there to make a double bond, shifted the one over to kick out that leaving group. So tomorrow, if you do show up to office hours, I'll go over how to predict the product quickly without doing this whole mechanism, right? Because there's a way to find the product without doing all this extra stuff. If this is a predicted product question to save time on the quiz, right? Okay, and that's gonna give us this final products here. This alpha beta unsaturated carbonyl, like that. Okay.
I see. Okay. This is that. Okay. That makes sense. That ending.
Yes. Okay.
Okay. Thank you so much. I'm gonna have to. You'll post this video, correct?
Yes,
so
I will.
Watch the steps. Okay.
Yeah, and practice too. Like watch the steps.
Yes.
Write out your own steps as you go along. Talk yourself through it, and do practice similar to this.
Okay. Perfect.
Yeah.
Thank you so much. I really appreciate it.
Yeah, of course, Madison. Yeah. Okay.
Thank you. Have a good day.
Yeah. Good night, Layla.
Good night.
Good night. Hey, Wiley.
I have one final question.
Yes.
In 118B or 118C, do you learn something called the Horner-Emmons-Wadsworth modification?
What is that? I have never heard of that.
I don't.
What is that? No.
Okay.
No, I have never heard of that before.
Okay, never mind then.
Okay, so for the first problem here, I saw that you have the E alkene, right?
Yeah, because there's resonance in the
This trick here that I wanted you to.
Oh wait, never mind. Yeah.
SP3 roadblock.
SP3
blocking resonance. It's okay. It's okay. Yeah, I just included there just in case a trick question like that shows up. You know.
Yeah, that legit might be a trick question. Oh.
Yeah, it looks tricky, but it's not stabilized. It can't do resonance, right?
That's
so
I should have drawn it the other way, where the ring should have been on the same side as it.
Right. Let's see. Double bond. Yellow. Blue. Now it's gonna be on the same side. CH2. Ester. Okay. Now for the second one that you have.
That one does resonance.
Yeah, this one is resonance stabilized. The E alkene, yellow, blue. Okay, and this one here, you put it an extra CH bond, right? So if this is your yellow bond, I usually yellow my carbonyl and my blue my ylid. I'm gonna draw the yellow bond carbon, right here, and blue right here, like that, which is attached to this phenyl group right here, right? You put a CH here, and then you drew that like that on that carbon, right?
I see.
Which is not the case. That the product that you gave earlier, right? Like which is this right here. Boom. This is the product you had.
Oh wait, I showed the correct number of carbons on the mechanism until the end, right?
And to the end, yes.
Okay.
Right. And I think it's because like you try to go for the E alkene. Like this is the E alkene right here, right? But in this case right here, we can't say E or Z alkene because those two groups are equally substituted.
Yeah.
So let me make this so we could put the E alkene. Let's say
that's actually a good trick question.
Purple group. Yes, I know.
You can't tell if it's E or Z. Okay.
Yeah, you can't tell it's E or Z because these two are equally substituted. That's good, right? So let's keep it a trick question like that. So then when you teach people this, you could give them these there.
Well, we learned this in like 20 minutes, and it was like so confusing.
Yes, I know.
Yeah.
But is this starting to make more sense now?
Yeah, it makes more sense.
That's good. Yeah.
Yeah. Jeez. Okay.
That's good. Okay.
I'll just screenshot it.
Okay. Yeah.
Thanks.
So yes, of course, really. Yes, I will see you maybe tomorrow if you show up, and definitely this Saturday.
Oh no, I can't do this Saturday because I have a field trip to go to.
Oh, okay, yeah.
It's for one of my classes, and it's worth my grade. Yeah.
Okay, yeah. Of course, yeah. Thanks for letting me know.
I can do it later during the night. But
oh yeah,
like 9 p.m.
9 p.m. Yeah, let me reschedule that and ask Ryan for that too.
Okay. Cool.
Yeah, that's good. Okay, good night, Wiley.
No problem.
Yeah. Bye bye.